Welcome back to the deep dive. Today, we are undertaking, well, a pretty intense exploration of what might be humanity's fastest moving problem.
We're talking about the collision course.
The collision course, exactly, between our just explosive technological expansion and the non-negotiable finite limits of planet Earth.
And this dive is so crucial because we're trying to move beyond just, philosophical worry.
Right.
We're getting into the realm of rigorous, cold mathematics. Our main source material here is a really stark systems analysis, and it's largely drawn from the work of the late Soviet astrophysicist Joseph Shklovsky.
And he used data spanning 1,000 years, right, from 1000 CE.
A full millennium. And he used it to project the dynamics of global civilization well into our current century, the 21st century.
So our mission today is really to gain that knowledge quickly and to focus on the aha moments that are kind of hidden in these growth curves and simulation models. Shklovsky pulled together his own analysis with the highly debated models from the Club of Rome, and he even used Arthur C. Clarke's, audacious technological timelines.
He did, and he built this comprehensive and, spoiler alert, a fundamentally unsettling picture of what unchecked progress looks like.
Stark picture.
It is, and we're looking at sources that were written during, a period of immense ideological tension, the height of the Cold War. But what's so interesting is they focused on variables like population, pollution, energy consumption, things that just transcended politics.
The underlying physics of civilization.
Exactly. The key realization Shklovsky forces on us is that the very law that's governing our growth is fundamentally unstable. It points to an unavoidable mathematical inflection point where the whole system just breaks. This dive is, well, it's a shortcut to understanding the realities those numbers reveal.
Okay, so let's unpack that. Let's start with the engine of it all. Human population growth. Shklovsky begins by charting global population over, as you said, a full millennium.
Starting around 1000 CE, yes.
And when you plot that, you expect to see things speed up. But the mathematical law behind the curve, that was the real shocker.
It really was. I mean, most people, when they think of runaway growth, they just think exponential.
Right, the standard curve.
And if population growth were purely biological, where the annual increase is just proportional to how many people there are, that would be exponential. You'd plot it on a semi-log scale, and it would be a perfectly straight line.
The signature of stable, predictable growth.
Precisely. But that's not what the data shows.
Not at all. When you look at the historical data, the plot just curves sharply upward. It's way steeper than a straight line. Humanity wasn't just growing, it was accelerating at an accelerating rate.
Which means the driver wasn't just biology. It had to be something far more aggressive.
So what was it?
Well, Shklovsky's surprising discovery was that for almost 1,000 years, our population growth fit a hyperbolic law with, remarkable precision.
N equals C over T0 minus T.
That's the one. And that mathematical signature is profoundly different from exponential growth. It represents a system with a powerful positive feedback mechanism, where the growth rate accelerates faster than the population itself.
Okay, so how do you prove a population curve is hyperbolic? You mentioned there's a surprisingly simple visual proof that kind of sealed the deal. How can you describe that for us?
The proof is, it's really elegant and undeniable when you see it. If the hyperbolic law is right, you do a transformation. Instead of plotting population n against time.
You plot the inverse, 1 over n.
Exactly. You plot the inverse of the population against time. And if the relationship is hyperbolic, that new plot must result in a perfect straight line.
And it does.
It does. Figure 52 in the text shows it clearly, confirming that for centuries, the human species has been operating under this runaway hyperbolic mechanism.
And once you have that perfect straight line for 1 over n, you can just extend it, right? You just extrapolate where that line is going to hit the x-axis, the time axis. And that extrapolation gives you T0, the exact moment when the math breaks down and the population, theoretically, becomes infinite.
And that is the moment of pure mathematical absurdity. The calculation, based on the data they had, it yielded this remarkably specific conclusion. T0 equals 2030, plus or minus 5 years.
2030.
The mathematical law that governed human growth for a millennium predicted that our population should hit infinity by the year 2030.
That's just a staggering number. And obviously, we didn't hit infinite population. The system has to break down long before that. So what is the core, the vital insight we have to pull from this impossibility?
The core insight is that because the conclusion is so manifestly impossible, it means the law of growth itself, the fundamental rule, must undergo radical, shattering changes within these few decades around the turn of the century.
So the trajectory itself is unsustainable. It's not just that we're growing too fast.
Exactly. It forces humanity onto an immediate, unavoidable inflection point where the existing growth dynamic must either fundamentally collapse or change. It basically defines the maximum lifespan of our current economic and social trajectory.
Which forces the question, why did this specific dangerous law persist for 1,000 years? What single non-biological factor kept that runaway curve going?
It's the factor of cumulative knowledge. That's what feeds back into population growth. The rate of population increase isn't just proportional to the number of people, n, it's proportional to the square of that number, n squared.
So it's a network effect.
The massive network effect. It happens because every person benefits from the collective infrastructure, the technology, the accumulated knowledge of the entire population. As Shklovsky puts it, if you have 1 million people, the amount of information and technical benefit they can all access is closer to the square of that number.
Because of communication and information systems.
Yes. That positive feedback loop, the cumulative power of our collective ingenuity, that's the real engine of hyperbolic growth.
And that distinction is just so key. I mean, if the natural biological growth law is the more manageable exponential one,
dN/dt equals alpha n.
right, where growth is proportional to population size, why are we operating under this highly unstable hyperbolic law where growth is proportional to the square of the population?
Because the hyperbolic growth is almost entirely driven by these powerful social factors. I mean, let's break down the difference. Exponential growth suggests that if one person has a slightly higher birth rate, that effect is sort of isolated and proportional to them.
It's additive.
Right. But hyperbolic growth, n squared, that implies a systemic multiplier. When a new medical breakthrough happens or a new agricultural technique is invented, that knowledge is shared and applied across the entire population almost instantly. It massively boosts survival rates and resource use for every single person.
So it's the difference between simple addition and this systemic compounding.
Precisely. The beta factor in that hyperbolic law is really a measure of human social connectivity and accumulated knowledge. If we were to overcome social crises, poverty, lack of education, global instability, theoretically, we could dampen that beta factor.
And restore a more normal exponential growth.
Exactly, by adjusting the proportional growth rate alpha. The crisis isn't some unalterable biological fate. It's a crisis of social dynamics that is manifested as runaway mathematics.
So the system is structurally prone to collapse because its engine, our knowledge and cooperation, is just too powerful for its container, which is Earth.
That is the critical conclusion. The solution lies in engineering a change in the social structure, the engine itself, not just accepting some biological destiny. The fact that it's socially driven gives us agency, but it also explains why the acceleration has been so hard to control.
So let's look at the other side of the equation, production. Shklovsky uses energy production as the most reliable index of our productive forces. How does that curve look next to the runaway population curve?
What's remarkable is how stable the energy curve is. Energy production growth, unlike that hyperbolic population curve, has followed a very stable, predictable exponential law since the late 18th century.
So it shows up as a much smoother, straighter line on the chart.
A much straighter line, yes. The doubling time for energy consumption has been reliably constant, about every 20 years for 2 centuries.
Which means our productive capacity was, mathematically at least, more stable than our reproductive capacity. And the genius of plotting them together is that you can immediately see the gap between them.
And that gap represents production per capita.
Right. And historically, that gap grew.
It did. Production per person was increasing because our technology was keeping pace. For a time, it was even accelerating faster than our demographic expansion.
Which led to this, massive global sense of optimism, the illusion that continued growth was manageable and would always lead to more prosperity for everyone.
But the chart's future projection, those dashed lines, they show that gap starting to shrink, or even reverse, radically.
So what drives that projected shift for the worse?
Well, first, the population growth in that era was heavily weighted toward developing countries. If that population continues to accelerate hyperbolically while also trying to industrialize and catch up in energy use,
which is only growing exponentially.
Right. Then the gap has to shrink and shrink quickly. But second, and more decisively, the production curve, while mathematically stable, is constrained by finite material resources.
A physical ceiling.
Once we hit that ceiling, the exponential growth of energy has to falter, while the demographic pressure just keeps surging towards T0.
So the one stable element, the energy curve, is about to get dragged down by resource depletion, while the unstable, hyperbolic population curve just keeps climbing towards collapse. That paints a devastating picture of that inflection point.
It really does.
So if the math is the engine, the environmental limits are the structural weakness of the container. Let's shift to this cosmic ship analogy. It's such a compelling, practical metaphor.
It's non-negotiable science, really. Earth is a large, incredibly long-lasting cosmic ship, but its resources are finite. The accelerating power of the crew has to conflict with those boundaries.
And we need to look at the physical limits that technology can't just wish away. You said there are two primary immediate dangers.
Yes, the limits of thermal output and the irreversible disruption of the biosphere's life support systems.
Okay, let's start with the heat. Not resources, but the sheer waste heat we generate. What are we talking about in terms of output and the implications of that 200-year trend?
So we're currently producing energy equivalent to burning about 5 billion tons of anthracite coal every year.
Which is a huge number.
It is. To put that in context for you, that's like continuously running nearly 200,000 of the world's largest nuclear power plants every second.
Wow. And that output has been doubling every 20 years for 2 centuries. If that trend holds, what's the 200-year projection?
It leads to a 1,000-fold increase in 200 years. And it could happen even faster, especially if we have a full-on energy revolution, a big shift to nuclear, because we're running out of coal and oil.
So solving the resource problem actually speeds up the thermal problem.
Exactly. And that leads directly to the heat barrier.
Which is what? How does that output compare to the energy Earth gets from the sun?
That projected output, that 1,000-fold increase, represents about 1% of the total solar energy that's constantly falling on the Earth.
1% doesn't sound like a lot.
It sounds small, but that much extra man-made heat added to the system will inevitably and fundamentally alter Earth's delicate thermal regime. It's the ultimate physics ceiling.
So if we cross that threshold, we're talking about global climate changes dictated purely by our own heat output, regardless of the energy source.
Precisely. Even if we switched entirely to the cleanest solar energy possible, Shklovsky argues the limit is probably no more than 1% of the total solar influx you can harness without, as he puts it, very unpleasant global consequences.
Changing weather patterns, disrupting ocean currents.
Significant increases in global temperatures. The solution to the resource crisis, infinite energy, becomes the source of a thermal crisis.
Okay, that's a long-term physics problem. But Shklovsky points out we are facing immediate, irreversible destruction of our life support systems right now. He says the crew is damaging the ship through unthinking activity.
He's talking about the oxygen balance, and he says we're attacking it from both ends, cutting supply and increasing consumption.
So we're doing 2 destructive things at once.
Simultaneously. On the supply side, the planet's main oxygen suppliers are ocean plankton and tropical forests. The analysis highlights that these forests are being, quote, predatorily cut down, especially in Africa and South Asia, with projections that the Amazon would be next.
And this was written decades ago.
Yes. And even then, that activity had already reduced the atmospheric oxygen supply by at least 10%. We're hacking away at the global lungs.
And on the consumption side, we're burning that 5 billion tons of coal equivalent, consuming oxygen and pumping out CO2. So how vast is the oxygen reservoir in the atmosphere? And why does that big number give us a false sense of security?
The total amount is truly immense, about 10 to the 15 tons. At current steady rates, it would take us 50,000 years to burn through it all.
Okay, so that sounds like we have plenty of time.
And that vast reservoir creates a dangerous lag effect. Think of the atmosphere like a massive 50,000-gallon water tank that's slowly refilling naturally. We're currently turning on a tiny faucet that's draining a fraction of a percent every day.
So if we dramatically ramp up the drainage rate now, which our hyperbolic growth says we will, the tank won't look empty for a long time, but the system's balance is already catastrophically broken today.
That's it, exactly. The consequence of the, say, 15 to 20% decrease in the equilibrium amount of oxygen that we've caused in the last few decades will only really manifest over the characteristic time for atmospheric dynamic equilibrium.
Which is thousands of years.
Several thousand years. That's why the problem feels distant, but the decision point is now.
But if we stay on that hyperbolic trajectory where consumption increases by tens of times in a century, the timeline just shrinks dramatically.
Absolutely. If we continue the exponential increase of fossil fuel burning, then the world's coal and oil reserves are more than sufficient for this suicidal deed, as he calls it.
And that leads to a catastrophic drop in atmospheric oxygen in just
A few hundred years. The scale of human impact, amplified by our technological growth, compresses millennia of natural change into centuries of engineered crisis.
Another critical system he mentions is the ozone layer, our shield against UV rays. And we know the culprit there is industrial waste, specifically Freon.
Yes, chlorofluorocarbons. The analysis gave some specific alarming details about how it works.
It's the sheer volume, isn't it? About 10 million tons of Freon were entering the atmosphere every year back then.
It's the volume and its chemical persistence. Once it's released, the Freon molecules mix, they rise up to the stratosphere, 20 to 30 kilometers up, and then they react vigorously with ozone.
And this is where the catalytic destruction happens, which makes it so much worse than a simple pollutant.
That is the critical detail. The Freon molecule isn't consumed when it breaks down ozone. It gets regenerated during subsequent reactions with free oxygen, so it acts like a permanent catalyst.
Meaning one molecule can just keep destroying ozone for years.
For years, even decades, it just accumulates its destructive power over time.
And what was the growth rate of Freon production at the time?
It was staggering, a 20% annual growth rate. That's a terrifying exponential curve applied to a persistent environmental destroyer.
And the calculation showed.
The calculations at the time showed that if that lack of control continued, the ozone layer thickness would start to noticeably decrease within just a couple of decades.
He used some incredibly vivid language here, comparing this to a crazy cosmic ship crew drilling holes in the walls.
And it's the perfect analogy. It was a perfect condemnation. We have been recklessly and knowingly compromising the fundamental integrity of our own life support system for, refrigeration and aerosols. The consequences are immediate and existential if that curve continues.
So all of these problems, thermal limits, oxygen depletion, ozone, they demand radical action. What timeline did the analysis put on making these changes?
The analysis states with, absolute certainty that only the adoption of the most radical measures within the next 2 to 3 decades could prevent the self-destruction of humanity.
Not a political cycle, a scientific deadline.
A deadline for a fundamental strategic change. And the first priority has to be an energy revolution.
A shift away from atmospheric combustion.
Towards atomic and solar energy. That directly tackles pollution and oxygen depletion. But, and this is important, Shklovsky immediately injects caution. He warns that while this solves the combustion problem, it inevitably introduces new, equally acute problems.
Like nuclear waste disposal or the thermal limits we just talked about.
Right. It seems like technology is both the cause and the imperfect cure.
So the ultimate guiding principle has to be bigger than just picking a technology.
It has to be. It has to be the constant acknowledgement of Earth as a cosmic ship with finite regenerating resources. And that dictates a fundamental shift from a strategy of exploitation to one of extreme regulated caution and management.
Treating our resources with the same care a spaceship crew treats its closed-loop system.
You have to.
Okay, to really grasp the urgency of this collision, we have to quantify the sheer speed of our technological engine. And this brings us to Arthur C. Clarke's Table of Human Achievements.
It's described as a bold and fascinating effort. It's Table 12 in Shklovsky's work, and it tries to map major achievements across 5 fields: transport, communication, technology, biology, chemistry, and physics, from 1800 all the way to 2100.
And it really demonstrates that our technological power is expanding super exponentially.
It does.
Looking back at the past, 1800 to 1960, the 19th and early 20th centuries were just an explosion of foundational science and engineering. What were some of the benchmarks?
The 1800s laid the groundwork. Steam engine, telegraph, atomic theory. Then at the turn of the century, you get the automobile, widespread electricity, X-rays, radioactivity, the birth of genetics.
And the pace just accelerates.
It accelerates so fast that by the 40s and 50s, you're into rockets, television, transistors, cybernetics, lasers. The historical review just shows this consistent, accelerating pace of discovery.
Now, Shklovsky generally accepted this historical overview, but he challenged the methodology, right? He said Clarke gave all these achievements equal weight.
He did. He argued that placing, for instance, the technology for extracting magnesium from seawater on the same level as discovering effective atomic energy was just flawed.
Yeah.
Atomic energy represented a fundamental change in our relationship with power and destruction.
That's a different scale of impact.
A completely different scale. His second critique was even sharper. He said it was impossible to put the discovery of the language of bees on the same level as discovering antibiotics.
You can see his point there.
Antibiotics had, quote, immeasurably greater significance for the survival and progress of humanity. They fundamentally changed demographics and life expectancy. The point is, technological progress is not evenly distributed in its benefit.
Okay, now let's cross the line into the predictive half of the chart, the future from 1970 to 2100. The analysis calls this catastrophically fast, almost explosive.
And Clark was pretty accurate on a few things, like predicting the lunar landing for the 1970s. For the 80s and 90s, he predicted huge leaps: gravitational waves, exobiology, artificial intelligence, and, crucially, thermonuclear synthesis or fusion power.
And the 2000s were slated for colonizing planets, a universal library, and weather control.
Right, and it's amusing that he thought colonizing planets might be easier than controlling the weather.
It's really telling, isn't it? It shows how hard it is to predict which challenges will fall first.
Absolutely. Colonizing another planet is an engineering problem. Weather control is a physics and computational problem of far greater complexity. And the fact that we didn't get cheap fusion power by the 90s shows how optimistic he was about fundamental physics breakthroughs.
So moving into the really radical long-term predictions, from 2030 to 2100, this is the period that coincides exactly with the Club of Rome collapse models.
And the capabilities become truly staggering. The acceleration is dramatic. By the 2030s, you see interstellar probes, contact with non-human civilizations, bioengineering. By the 2050s, we move into physics mastery, control of gravitation, planetary engineering, terraforming.
And then the 2060s and 70s are concepts like destroying space-time and near light speeds.
And the last third of the century is basically the ultimate tech fantasy: a global brain, astroengineering, and scheduled for 2090, immortality.
Let's focus on the extraterrestrial contact predictions, because that's where Clark's optimism really clashes with Shklovsky's skepticism as an astrophysicist. Clark predicted radio contact in the 2030s and a physical meeting around 2100.
And that timing is very revealing. If a physical meeting happens in 2100, after a starship launches around 2080, it implies the nearest inhabited planetary system has to be within 20 light years of Earth.
He's assuming a very high density of civilization. Almost every planetary system must be populated.
He was operating on a best-case, highly populated galaxy scenario. Shklovsky, based on his own research, was highly skeptical.
Right.
He argued the nearest civilizations are likely hundreds, maybe thousands of light years away, 10 to 50 times further than Clark's model implies.
So that massive distance just pushes the date of any meeting way into the future.
It does. It shifts the limiting factor from our technology and speed back to the objective reality of astronomical distances. Clark focused on our accelerating speed, but Shklovsky focused on the immutable limits of the speed of light and the probable density of life.
And what about that immortality prediction for 2090? If our lifespans extend by a factor of 10 or 100, doesn't that just make the resource crisis even worse?
That is the paradox of technological progress in a closed system. Shklovsky clarified immortality really means substantial life extension. And while that's a biological triumph for the Club of Rome models, it's a complete disaster.
More people living longer means the hyperbolic curve hits the resource ceiling even faster.
Exactly. It fundamentally shifts the goal from indefinite survival to a state of perpetual managed scarcity.
So whether the dates are accurate or not, the overall trajectory of Clark's chart leads to one undeniable conclusion that really ties back to that T0 equals 2030 problem.
The chart demonstrates that by 2100, human technological capabilities, planetary engineering, astroengineering will have substantially outgrown the modest, finite resources of Earth. The sheer scale of power we'll have will necessitate a planetary-scale strategic change.
And this technological surge is described as a non-equilibrium process. What does that mean for us strategically?
Humanity evolved within the biosphere, in a state of relative biological equilibrium. Our technological explosion has fundamentally forced us out of that state. We're now in a system that is fundamentally unbalanced and accelerating towards collapse.
So our whole future hinges on making a conscious choice.
A critical conscious choice to abandon the strategy of unlimited super exponential growth and adopt a fundamentally different behavioral strategy.
And if Clark's chart gave us the speed, the Club of Rome models provided the operational mechanics of that collapse. This was a pioneering effort using system dynamics to model the future.
And it was deeply controversial. because it crossed the line from pure science into political economy.
That's vital context.
These studies, using computers to solve thousands of simultaneous differential equations, they recognize the complex interconnectedness of everything: population, resources, industrial production, pollution.
You can't solve one problem in isolation.
Exactly. Every variable affects every other variable over time.
Yeah.
This wasn't just science, it was a deeply political statement about global economic policy and the limits of free market capitalism, which made it an instant target.
And their first step was a really sobering assessment of the planet's hard resources. And they included a huge mitigating factor, right? They assumed known reserves would increase fivefold.
A massively optimistic assumption, yes, to account for future discoveries.
Yeah.
And even with that optimism, the depletion timelines remain terrifyingly short.
So what were the resources with the shortest estimated lifespans?
Things like natural gas, about 49 years, oil, 50 years, copper, 48 years, aluminum, 55 years.
So the fundamental building blocks of industrial civilization, aerospace, electronics, energy, plastics, all gone within the lifespan of a single person.
And even the longer-lasting resources like coal, chromium, iron, they still have finite limits well within the next few centuries. The analysis concluded that the finiteness of Earth's resources, combined with progressive pollution, is the single decisive factor in our future.
It's not ideology or war, it's resource accounting.
It's just accounting.
And to really drive home the acute nature of the damage, the analysis uses two dramatic real-world examples. The first is oxygen depletion in the Baltic Sea.
Yes, figure 53. It serves as a perfect localized warning. It tracks the oxygen in the water near the bottom of the Baltic, showing a precipitous drop from over 30% in the early 1900s to near zero by the 1970s.
The source says it became essentially dead.
And it's a stark illustration that when pollution overload hits a critical local threshold, the ecological system just collapses quickly and unpredictably.
The second example shows the massive economic barrier to actually cleaning up our mess on a global scale.
Right, the cost of purity. We can filter waste, but the closer you get to true cleanliness, the exponentially more expensive it becomes.
That's the critical economic insight from Figure 54. The cost curve isn't linear, it rises sharply and exponentially as you approach 100% purification.
Exactly. Getting to 10% purity might cost almost nothing. But to reach 90%, the cost skyrockets to over $90 per kilogram of material processed. Achieving 99.9% is often technologically and financially impossible on an industrial scale.
So that exponential fiscal barrier basically guarantees that even if we want purity, our economic models will stop us from getting there.
It does, which sets the stage for their first scenario, the Standard Model. This is the projection of what happens if humanity just continues on the current path.
The do-nothing scenario.
The do-nothing scenario. The variables are resources, P, food, ale, and esh, industrial production per capita, PR, and pollution, Z.
And the model shows growth continuing right up until the early 21st century.
Exactly. Hitting that T0 equals 2030 inflection point we talked about.
So describe the trajectory after 2030. What's the causal chain that leads to the crash?
It's a devastating chain. Resources, P, deplete steadily. This scarcity spikes prices, which forces a reduction in industrial investment, PR.
And because food production is so dependent on industrial inputs,
fertilizers, machinery, energy, the food supply quickly stalls and then plummets. Following food, both industrial production per capita and population H begin a swift, sharp decline around 2040.
and pollution, it spikes dramatically right before the collapse.
Pollution, Z, spikes because industry is forced into cheap, dirty methods as resources get scarce and expensive. The crisis moment is when this system crashes. Production, population, and food plummet rapidly by 2100. The lines approach zero,
The trivial stationary solution.
which the Soviet authors later mathematically described as the system's death state. The model guarantees the current economic structure doesn't slow down gracefully. It hits a hard wall.
So the ultimate warning is that the current trajectory leads to mathematical zero.
It proves that the exponential mindset cannot survive contact with a finite physical world.
The next two models test whether massive technological breakthroughs can save us. Model 1, unlimited resources, asteroid mining, fusion power, everything. What happens then?
The collapse just gets shifted. If you remove resource depletion as a factor, industrial production explodes even faster. But because that unbounded growth requires vast manufacturing and energy, the driving force for collapse becomes catastrophic pollution. Pollution spikes higher and faster than in the Standard Model because production is now unlimited. And this pollution is what ultimately causes population and production to decline violently.
So solving one problem with technology only makes the catastrophe worse if the fundamental growth strategy is unchanged.
Exactly. Technology only changes the reason for the collapse, not the certainty of it.
Okay, so Model 2 tries to fix that. It adds massive investment in pollution control on top of the unlimited resources.
And even with infinite resources and significant mandated investment in that exponentially expensive pollution control, the collapse is only delayed.
It still happens.
The system is sustained a bit longer, but the sheer effort required to maintain high purity and support the vast population overwhelms the system by the latter half of the 21st century. The core lesson holds. You have to exit the growth dynamic.
Which led the Club of Rome authors to propose their highly controversial solution, a complete shift to an equilibrium civilization.
A zero-growth strategy. It assumed absolute zero growth, both population and industry, and precise, total regulation of all productive forces.
And the intervention dates they suggested were
Strict birth control implemented globally starting in 1975, and a complete halt to industrial growth starting in 1985. We have to remember, those dates had already passed when Shklovsky was updating his work.
right, highlighting just how politically difficult that would be. So what did this extreme mandated stability actually achieve in the model?
Figure 58 shows it only managed to postpone civilizational collapse by 2 to 3 centuries. It gave humanity hundreds of years of stable population and industrial production.
But because resources, even if strictly managed, are still finite.
They continued their slow depletion over the very long term, eventually causing the system to decline anyway. Equilibrium buys you critical time, but it doesn't offer indefinite stability within a closed system.
So the Western models concluded that either we collapse quickly or we collapse slowly. Collapse is the mathematical fate of a civilization trapped on Earth.
That was the conclusion, based on their modeling structure. It was fatalistic, and it assumed specific political and economic constraints, namely the constraints of a capitalist system that can't easily divert huge sums of investment away from profitable growth and toward mandatory remediation.
And this is where we find that fascinating deep dive nugget. The Soviet authors, Gelovany and Igorov, they challenged this Western fatalism on mathematical grounds.
Yes, they mathematically proved that the Club of Rome models lacked what they called non-trivial stationary solutions.
Meaning the only stable state in those models was the death state, where all parameters are zero.
Exactly. They argued the fundamental structure of the Western models was inherently biased toward collapse because it didn't sufficiently account for regenerative investment.
Which speaks to the ideological context. The Club of Rome models were implicitly built on Western market assumptions: investment follows profit.
And the Soviet models were built on the assumption of a centrally planned, regulated economy where investment could be mandated for the common good, regardless of profit.
So if stopping growth doesn't prevent the crisis, what did the Soviet authors propose under their centralized system?
They proposed a model where collapse is eliminated not by stopping growth, but by intelligent management of investments.
Okay.
They showed that if a very large portion, maybe 40 to 50% of investment, is continuously directed toward fighting pollution, restoring resources, and eliminating arable land erosion, the system can achieve non-trivial, stable solutions.
It shifts the focus from stopping the flow to managing the system's regeneration capacity.
This is the definitive cosmic ship regime. Growth can continue, but only if the rate of investment in regeneration and anti-pollution keeps exact pace with the rate of production and depletion.
The philosophical difference is profound. The West sought stability through stagnation, zero growth. The Soviets mathematically sought stability through managed, sustainable, regenerative growth. But despite the elegance of that alternative, Shklovsky still seems skeptical that it fully solved the problem.
His final conclusion reflects that skepticism and the immense pressure of the timeline. He stresses the urgency. Only a complete, immediate halt to production growth and severe resource regulation, coupled with spending the lion's share of national product on anti-pollution efforts, offers a viable, immediate solution.
He comes back to the harsh reality that the delay effects of decisions we make today are measured in decades.
We have to change our strategy now, without waiting for the political will required for either the Soviet or the Western solution to fully materialize.
So the decision to change from a strategy of unlimited growth to one of balanced, managed regulation is the defining crisis of modern civilization. And the math says the clock ran out around 2030.
The system has been forced into an inflection point where the old hyperbolic law can no longer apply. The choice is between self-engineered collapse and a radical resource-managed global system.
This has been a profoundly rigorous analysis. We've moved from 1,000 years of demographic data to a forecast of 21st century civilization. We've established the mathematical inevitability of the crisis through that hyperbolic law.
The system must change.
We've seen the physical urgency through the irreversible destruction of the biosphere and the ultimate economic fatality of all the standard models.
And we learned that even the most optimistic technological fixes only delay the inevitable collapse if the fundamental strategy of growth remains unchecked. The only stable future, whether through equilibrium or intelligent investment, requires humanity to move to a strict, regenerative, cosmic ship regime.
And what's so fascinating and the ultimate provocative thought for you, the listener, is that every single argument we have covered, the hyperbolic law, the thermal limits, the Club of Rome simulations, they all hinge on one single assumption.
That Earth is an isolated small planet with fundamentally limited resources.
That's the strategic shift.
Shklovsky subtly hints that the only true path forward, the one that escapes the harsh limits implied by T0 and the collapse curves, must lie outside this closed terrestrial system. All these dire warnings apply only to a civilization bound to this one planet.
So if our capabilities are destined to outgrow Earth's resources by 2100, as Clark's shirt suggests,
What are the implications of the next strategic shift? The discussion of development beyond our isolated planet, touching on large-scale planetary or astroengineering, that's the only potential escape from the mathematics of terrestrial doom.
a compelling note to end on, suggesting that our survival might depend on us embracing the very explosive technology that created this crisis, but directing it outward. Thank you for guiding us through this urgent deep dive.